Okay, the moment you've all been waiting for. Let me open up the script. This is the maze solving and multi-destination path optimizing and visualizing robot simulation built visualizing a pre-existing GUI. So I developed a versatile robot inspired by the Micromass competition capable of solving mazes, optimizing multi-destination paths, and visualizing its progress. Let's have it running in the background at full speed. Just reading off the script, I conceptualized navigation solutions starting with small goals like vertex creation, which you can see labeled with numbers in different colors, yellow meaning unexplored, green meaning explored. I started with small goals like vertex creation and neighbor navigation. So when it hits 8, what does it do? It goes to north, east, south, and west, exploring its neighbors until it hits another vertex, and you know populates a stack of nodes to explore based on current distance and stuff like that. I modularized functions for movement, distance tracking, orientation, and location classification using sensor data. So this little blue robot you see going has these proximity sensors. Really, they're functions that I call to check if there's a wall on its immediate left, right, or in front of it. Meaning like one unit away, so it only checks if it has if there's a wall immediately in front of it. And then I utilized the visual tools in this this API that allowed me to color each of the cells and label each of the cells. So I did maze location color coding and labeling and constant feedback, which you see on the right hand side, which I used as I developed this solution. Let's see if we can keep this video going. I also implemented suboptimal procedures initially, such as, let's say right now, I didn't really we're going from like 22 to, I don't know, we're going from, let's say, 22 to 23. You'll see it take the optimal route, right? But initially I did that suboptimally, but like a surefire way of doing it. The surefire way of doing it is to go from your source all the way back to the home, to the origin, which you can do by backtracking, and then go from the origin to the destination by backtracking from the destination and then flipping that order and then going up there. So it was just always go to the origin, then go to the destination, and it worked. It allowed me to get to make progress. And then once the little blue robot was solving the maze and successfully, I decided to optimize by introducing another maze solving algorithm within this vertex to vertex travel. I opted for Dijkstra's, but no, I could explore different. Oh, here it goes. I could explore different maze solving algorithms. Like, yeah, there's room for research. I could compare them, um, have them run, and then color their paths differently and record their time, and just sort of research the different path searching algorithms. Right now, what you see is it traveling between randomly generated points, not just between the start and the end, which is a function I added at the end, right? So I enhanced the program with a random travel between any 2 points. So right here you can see it ended up in just a random point, not one of the vertexes. Vertex being identified by like a location in the maze that has multiple openings. So from 7 we can go north, west, and south. But from these points with a dot, you notice you can only go in one direction, like north. If you know what I'm saying. So, and then about the big tagline of multi-destination path optimizing, interestingly enough, ties into a class I'm taking right now called linear optimization, where we're exploring the traveling salesman problem. And that really got me thinking, like, when you were doing something like the traveling salesman problem, the way they go about it is, well, they use this certain approach, um, um, and what they do is they basically try a permutation of the ordering of the destinations, um, but they include pruning. which kind of strikes me as like an obvious way to optimize now, because the way I thought about um, doing multi-destination path optimizing is I could just track the costs of my destinations permuted. So maybe I go ABC or ACB, or if I have more destinations, if I do 4 destinations, then it's there's 3 factorial possible ways to go from A to B, C, and D. I can go A, B, C, D, A, B, D, C, A, C, B, D, etc., etc. And what I can just do is I can calculate the cost to do those trips and then just go with the best one. But you can optimize that. I realized it taking this class while we were talking about the traveling salesman problem with a little bit of pruning. So what you do is I don't know, like be an interesting algorithm to implement, like that. Maybe I should do that over the summer. But anyways, the way it works is, and I just did homework about it, is like imagine a tree, and you're starting from A and you're going to B, C, and D. Right now, what you're trying is what second destination you arrive at, and let's say you from A to B and A to C and A to D, you get your cost. What you then do is you go with the lowest cost. You branch out in the direction of your lowest cost. So now from C, you check how much it costs to get to B and D. And now your tree goes A, B, C, D, B, D, extending from C. And then suppose that the cost to reach B through C, so ACB, is still the minimum cost amongst all the leaves in your tree. You continue to branch in that direction, and it's sort of like an efficient way of doing what I thought was like the brute force. I mean, the brute force way of just permuting your destinations. It's like a way of it's just an intelligent way of an algorithm of finding your optimal solution, which I don't implement here. I just kind of did like a thought exercise about it. But there's that. There's that. Hopefully, you got to see a little bit about how what I think about this project and how I go about it. Then there's also the idea of like saving information, which got me thinking about like Google Maps. Like they must save in some database, you know, paths between destinations and stuff, and not recalculate it every time someone prompts, the Maps app. And yeah, maybe there's just things I could like data I could save every time I run this app. It just restarts. But I could save all the data, and then it just got me thinking. Like companies like how FedEx does their thing, how they deliver all their packages. They just do their traveling salesman problem, don't they? And how Google Maps works. I mean, it's all like insane engineering, right? Isn't it? But yeah, this project gets me into that headspace, so it's fun. But for now, the project's done, and I hope you enjoyed watching this. So see you later. Hope you enjoyed.